So today in this video, what I'm going to do is just spend a few minutes reviewing all of the sort of basic, most important properties of mechanical waves. And in particular, I'm going to be sticking to one-dimensional waves. So what is a mechanical wave? Well, we know there's all different types of examples of mechanical waves: ocean waves, waves on a string, sound waves. But these are all basically traveling disturbances through a medium. And I phrase it in that sort of weird, precise way for a couple reasons. So the first part, so I said it's a traveling disturbance. And that's really to point to the fact that in a wave, really any type of wave, it's really a disturbance that's traveling. It's energy that's traveling. It's not the material itself. And so again, so I also said that word material, or so through a medium. And that's because if it is just a traveling disturbance, it needs something to travel through. And so mechanical waves, these are different from electromagnetic waves, which do not require a medium to travel through. Mechanical waves do require a medium. So we have a wave on a string, we have a wave, a pulse that you send down a slinky, we have ocean waves where the water is then the medium. So mechanical waves are traveling disturbances, again, because if you send a pulse down a string, the individual particles in a string aren't really moving a great distance. It is just the disturbance that is traveling through the string. So anyways, so mechanical waves are basically a traveling disturbance through a medium. So I'm first going to give some sort of general properties that any mechanical waves, these are things that would apply to any mechanical wave. So there are two types that you could consider. You can consider longitudinal or transverse. Or really there are more types because you could consider combinations of these. So of course transverse waves are where the disturbance is perpendicular to the direction of motion of the wave, and the longitudinal ones are where the disturbance is along the wave. So examples you could think about are, so a slinky. So when you send a pulse down a slinky, the slinky itself sort of vibrates this way along the direction the wave is traveling. Or a transverse, so this is like a string. So if you send a wave down a string, you sort of lift it up, you send a pulse down, and the propagation is actually transverse or perpendicular to the direction in which the wave is moving. And then I guess I should say, so maybe three types. You can have mixed. So this is like ocean waves. Ocean waves are actually sort of some complicated combination of transverse and longitudinal waves. So the first thing about waves is you could consider these different types of displacements. The next sort of most important defining property is that they satisfy a wave equation. So this is the differential equation that any wave must satisfy in order for you to even be able to call it a wave. So this is the where y of x and t describes the motion of your wave. Or I should say it's really the displacement. It's a measure of the displacement. So y is your solution to this equation. That's what you're solving for. And then this v down here is the velocity. of your wave. And maybe I'll add at this time, because I just mentioned the velocity, is that another very important thing to note is that the velocity is only medium dependent. So that is to say, the velocity at which your wave travels only depends on whatever it is traveling through. So if you send a wave down a string, that's going to depend on the particular properties of that string, so how dense your string is, and just the fact that it's a string at all. The velocity for a wave moving down a slinky or the velocity of an ocean wave are going to, so it'll depend on properties of your ocean or properties of your particular slinky. And it's not going to depend on other things such as the amplitude of your wave, which we'll discuss a little bit more. So a general solution you can show, the most general solution to this wave equation, so again, this means any wave, anything that you can actually call a mathematical wave, which is a solution to the wave equation, can be written as y of x and t equals some function of kx plus or minus omega t. So you could have two different functions, where here k and omega are some constants, but any general solution can be written in this form, where f and g can be different functions. And basically the two of them are representing a right-moving and a left-moving wave. So you could write all sorts of crazy things as long as they could be expressed in this form. All right, so the other sort of general properties of waves. So we have this multivariable function. We could consider taking partial derivatives of it. So if we take the partial derivative of the displacement with respect to x, or you could take it with respect to time. So if you take it with respect to position, then this is going to give the slope of the waveform. So what this really means is if you take a photograph of your wave at some particular time, then the shape of that photograph, the shape of your wave in that photograph, is the waveform. And this will give you the slope. If you literally just calculate the slope at each point, this partial derivative will give you that. And the next is the partial derivative with respect to time, which gives the speed of individual particles. And so sort of what I mean by that is, so what I said is a wave is a traveling disturbance. If you send a pulse down a string, it's really the disturbance that's traveling a great distance. And this velocity here is the velocity of that disturbance. Now, you know that also, especially if you're sending, for instance, a sinusoidal wave, which we'll discuss more in a minute, what really happens, so if you're sending a sinusoidal wave down a string, you're moving it up and down, then that means the particles are just standing there. They aren't traveling right to left, but they're moving up and down. And you could compute a speed of that. And so this partial derivative of y with respect to t is sort of the speed of your individual particles. And so these are all the sort of general properties of waves very generally. So you could have any wave of any form, and all of these things should apply. Now there's a very particular class of solutions to the wave equation that come up a lot, and I just said the word, which are sinusoidal waves. And it's always really important to keep track of, if you have a particular expression describing a wave, whether this expression applies to waves in general, or whether this is something that only applies to sinusoidal waves. So now I can draw, since I have a particular solution I'm considering, I could draw the wave. So I could consider drawing it at fixed time or fixed location. So what I mean by that is at fixed time, this is like taking a photograph of some sinusoidal wave, and then I'm plotting the height of the wave with respect to position at this particular time. So again, this is what a photograph would look like, and maybe your sinusoidal wave will look something like this. And then instead, I can plot I could consider a particular point on, let's say, this string, if this were a string, and now I want to plot its motion as a function of time, so just one little point. So now I'm going to fix a location of this multivariable general solution, and a sinusoidal wave then might look something like this. So things that you can read off of this graph, so there's a lot of information you can get from drawing a plot like this. So the first thing is the amplitude, so I'll call that y sub m, which is the maximum displacement your wave might have, and it's going to be the same on both of these plots. You could also, in the fixed time situation, you can read off what the wavelength is. So if you look at one complete wavelength, then you could read off, so the distance from here to here is your wavelength. In the fixed location, so this is a plot in time, you could read off then, so from here now all the way to here, you could read off one period of your wave. And this is all information that you can gain by even just looking at a picture of what it looks like. So let's say, I guess I could give you, I haven't actually given you a mathematical expression. So as I've drawn them, this sinusoidal solution might be something like y of x and t equals this ym, this maximum amplitude of, sorry, I'm going to scratch that, of sine of kx minus omega t. So I've drawn them such that there's zero phase, but in general you could have a plus phi over here, which would shift these from right to left. And then the final, so the other properties of these sinusoidal waves that you could write down. So we already have the wavelength, the period, so we know the frequency is 1 over the period. You can also define an angular frequency, omega, which is 2 pi times the frequency. You could define something called the wave number, which is often represented by the letter k. That's 2 pi over the wavelength. And then in order for this to be a solution of the wave equation, so the wave equation, we haven't really, this doesn't have this velocity that showed up here at all. But this is actually related, and in order for this to be a solution, or really for these, so actually maybe I should write this here, these are only a solution if these two constants, k and omega, which in general can be, whatever you want them to be, and only represent the wave number and the angular frequency in the case of sinusoidal waves. This is only a solution if the velocity is equal to, let's get this right, omega over k. So I'll write that again. So the velocity of your wave is equal to omega over k. So all of these things are related to each other, and so it's really important to remember how all of these constants are related to sinusoidal waves. All right, so that was a quick review of mechanical waves. This is really most of the things that you need to know. If you want to think about things like standing waves or the power transmitted in waves, then I'll have some different videos discussing those other properties of mechanical waves. But other than that, this is the big picture. So thanks.